All right, let's talk about verifying Green's theorem. Verifying is different than just using Green's theorem, leveraging it to find this line integral. It means that we need to find both the area described by this line integral, which is an area under a surface along a curve, and we also need to use Green's theorem to show that this is the same as summing up all those itty bitty bits of curl within the region that's enclosed in this simple connected curve. So first and foremost, if we're going to do this, the easier way to deal with is normally Green's theorem, right? That's the whole point of Green's theorem, is it takes a complicated line integral and makes it into a simpler double integral over a region. So in general, we need some stuff. Green's theorem tells us that if we have some p dx plus q dy, representing, of course, a vector field defined by p and q as functions of x and y, then we can rewrite this as the double integral of the enclosed region, because we're in a simple closed loop, of the partial of q with respect to x minus the partial of p with respect to y. This is our curl for that entire area, right? So that's what we need to do first. Okay, we recognize our p is equal to xy. So our q is just y. The partial derivative of y with respect to x is 0. Our partial derivative of xy with respect to y is just x. So this is our very first step. I have rewritten my line integral as a double integral using Green's. Now, I need to actually think about what this closed simple loop looks like. What is my region? Because I have to go from a curve to a region. I didn't bother to write it down, but in this case, we're going to do the simple closed loop where our C is equal to the unit circle, and we are traversing that unit circle in a counterclockwise fashion just to make life easy so that it matches Green's theorem. So here's our beautiful unit circle, and we're going around this in a counterclockwise direction. Now, two ways we can set this up. We can just go ahead, stay in rectangular land. Most of us, the moment we see a unit circle, are not staying in rectangular land. We're going, oh, yeah, I know how to reparameterize this. In this case, x is equal to our cosine of theta, y is equal, we're going to use polar. I don't really need to reparameterize, but instead of redoing this in x and y's, I want to just deal with the fact that for a unit circle, if I do this in polar, I need my r, and I can see my r is between 0 and 1. I did have a couple of students, maybe one or two, who still had that negative 1-to-1. We're not paying attention to how polar. We always are using strictly positive values for our r and our theta. Well, we need to go all the way from 0 all the way around to our 2 pi to make sure we get the entire unit circle. So if you're in polar land, that's what we need to do. We also need to recognize that our xy in polar land, dx, dy, that dA becomes an r, dr, d theta because of that Jacobian when we change the variables of rectangular to polar. Then we could have brought this all together to rewrite this region as, okay, 0 to 2 pi and 0 to 1. Those are my two bounds, right? We're going to have r, dr, d theta. And then I do need to convert everything to be in terms of polar, so I can't leave an x floating around. I got to use that polar conversion to go between our x's and y's and our r's and thetas. So we have a negative r cosine theta. So anyways, this all ended up being a negative out in front, r squared cosine theta. I left off a dr. And then we knew how to work through these double integrals. So we should have ended up, after some work, at a negative 1/3 sine of theta evaluated at 2 pi and 0, which gave us out 0. I do want to show you, had you stayed in rectangular, it actually worked out as well. One student chose to go this route. So if I stay in rectangular, I would need to think of this as either horizontally or vertically simple. It is equally simple in either direction, so I'm going to go ahead and go with vertically. I do need to think about the actual equation for a unit circle. x squared plus y squared is equal to 1 if we're in rectangular, which means this y is going to be between the square root of 1 minus x squared and negative square root of 1 minus x squared. So a different way to come from here would have been, okay, I end up with negative 1 minus x squared, 1 minus x squared. I can leave the negative x here. dy was the first. And then my x's, I need to go from negative 1 to 1. This one actually did not work out as bad. Usually we avoid this because we don't want the silly square roots, right? They can get kind of nasty. But if we actually did this one at the very first plugging in, you ended up, I think, perfectly fine with things canceling, or maybe you had to do use of, I don't know, but you could have actually done this. It's not bad because in that first step where you get a dy dx, you're going to end up with something you could use sub later on. So if you went this route, we could also end up with 0. Okay, one last thing before we move on to the verifying part, doing the harder part, which is the line integral. That would be, I want to mention the idea that just because this is 0, that doesn't mean we ended up with a conservative vector field, right? We know for a fact we didn't have a conservative vector field, because if we wanted to check for a conservative vector field, that would mean that this f, that vector field, is a gradient for some potential function we don't know, but we could go back and get. And if that is true, we can use that theorem, can't remember which person is named after, that tells us our mixed partials can happen in any order. So if that's true, this was already theoretically, I used p, which is what, v for the, we'll use v for the potential function. This was some dv dx, partial of v with respect to x, and this is partial of v with respect to y for my q. What should happen is my partial of p with respect to y, that's the mixed partial, should equal my partial of q with respect to x. The fact that there's anything at all here means that this was not a conservative vector field. So we ended up with an area under the curve that's 0, but not because our vector field is conservative, just for another reason, right? So don't assume, we're not guaranteed. Conservative gives us 0 for that line integral in a closed loop, but just because you get 0 in a closed loop does not mean the original vector field is conservative. All right, so let's do the verification. So the last thing we need to do is actually calculate this line integral. So I'm going to rewrite our line integral. xy dx plus y dy. There are two ways to do this, but no matter what, we know for all of our line integrals, we reparameterize in terms of another variable, usually t. And so let's go ahead and write down our curve again. Our curve was that unit circle. We know the best way, hopefully, to parameterize our unit circle is to use x is equal to cosine of t and y is equal to sine of t. If you wanted to use theta, you could, but we typically use t. This is going to give us the unit circle, and it's going to let us go counterclockwise, which is what we wanted. And then we do also need to recognize that our t, we're going to start at 0, go all the way around to 2 pi. I had a couple of students who had that t off. They just went from 0 to 1. All right. Now, there are two ways now to handle this question. Most students did this, which is, hey, we know how to find a vector field. We don't even need the little closed loop indicator. We know how to find a line integral of a vector field. We need to reparameterize our vector field in terms of t, and then we'll do a dot product with the derivative of our vector value function that gives us that curve that we're following, right? Now, here's where things got weird for a lot of students. We were really good about plugging in cosine of t and sine of t for x and y above, right? We had some issues with writing out this vector field. Like, first and foremost, we're doing a dot product. So these need to be vectors. So if I'm plugging in for this, I need to recognize the original vector field here is x, y, comma, y, right? That was the original vector field that's already been dot product in this particular way of expressing it. And so when I write this out and I go, okay, I'm from 0 to 2 pi, and I got this, I got my cosine t, sine t, sine t. I needed this to be a vector. A lot of students had a plus sign here. And while there's a plus sign in the original problem, that's because they've already done a dot product. And we need this to be expressed as a vector if we are going to do a dot product. So no plus sign allowed, right? The next place students got in trouble was figuring out what the heck r prime of t was. A lot of students wanted to just take the derivative of that vector field, but we need to talk about how that we're moving through the vector field. We don't want the vector field's derivative. We want how our tiny curve is changing over time, right? So because we didn't take the time to write down r of t is this thing we just found. This is how we travel along this curve. Because we didn't have that written down, we got in trouble. Now it's easy to find r prime of t, right? This is negative sine t cosine t, but we didn't have that. And so that was, I think, the failing for a lot of students moving through this format. Now, unfortunately, this format is actually harder when it's already expressed as a dot product, a finished dot product. That's what this is. This is the finished dot product version of f of, times this derivative, like c dot. I don't want to write it there and make this untrue, but we'll see it right now. So a different way to handle this is, hey, we know x and y, which means I can take those derivatives. In fact, I already have them right above. This is negative sine t dt, and dy is equal to cosine of t dt. And I can just plug in all of this stuff. Everything in green plugs directly into the line integral over there. So I can go, okay, this is equal to 0 to 2 pi, because I know that's the bounds on my t. X was cosine of t, y was sine of t, dx was negative sine of t. There's a dt running around, plus y was sine of t, and dy is cosine of t dt. This is literally what you'll get if you dot product these two things. Same. These are the exact same thing. So then we're able to come back and say, okay, now we're here. A lot of students split this up into two integrals. Not necessary. In fact, I'll go ahead and put my negative sign back. Negative sine squared t cosine of t plus sine of t cosine of t dt. No matter what, you needed to do a u sub. There was no trig identities needed. If you made u equal to sine of t, du is equal to cosine of t dt. We've got all of that stuff. You ended up here, negative u squared plus u du. If you actually plugged in to change the bounds on this, you immediately got your answer because you found that your bounds are now both 0, right? Sine of 0 is 0, sine of 2 pi is 0. I don't need to take an antiderivative or do any fundamental theorem of calculus stuff because I know the area for a single integral, when we haven't actually moved anywhere, if we don't have any area, this is 0. This is one of the properties of integrals. If the bounds are the same, we're done. So we get out the same answer of 0 that we did in the other version.